Hello, welcome everyone to another video about my PNS scripts. Sorry for being naked, it might look a little bit weird, but in my country there is like thousands degrees at the moment, so there is really no point in wearing clothes. Sorry about that. So what I will be talking about today is this little curve here, which obviously produces a randomized signal that can have a rate between 20 Hertz, so really fast. And yeah, this is actually not 0 Hertz, but something that is very close to that. Obviously you want to use this as a modulation source because it is a randomized signal, and you know, I'm working on this vibrato that has a randomized curve, and it uses a very similar technique to this. So basically what I was doing up until now was I created a signal that just consists of a randomized value, and in regular intervals a new randomized value is picked, and so on and so on. And after that signal was made, I applied a low pass filter to that. Actually, let's draw it a little bit differently to bring a point across. Low pass filter, okay, good. Because what often happens when you have a low pass signal from another signal is that the level drops. So we had a maximum at this point and now it is here. And the problem is, since IIR filters are kind of weird sometimes, it is really hard to measure where exactly is the point where the new maximum gain is. I don't know if it's even possible at all, because they have a lot of to do with infinity and stuff with this feedback loop and everything. I'm really not a filter expert. So I was asking myself if there is a better way to kind of get a random curve where I exactly know where the maximum point is, because then I can be much more free for different things. So let's say we have two lines that kind of express the maximum values, and then we choose random values, and the random values can be there. And then the idea is that we just use some interpolation method for drawing the curve, like spline interpolation. In this case, a Hermit spline, like I always use when I just try to test something curvy really quickly and stuff. Yeah, so basically this. But there is a little problem with this that will occur, and I can already spoiler you what it is. When you have a very rapid change in the signal, then it can be that the spline interpolation thinks that you want to do something like this, and then you have some overshoot. So now we have a new problem. We had the last problem was that a low pass signal does not even reach the maximum, and the new problem is that we can exceed the maximum. But now we have a little advantage here, because we can actually measure what the overshoot of the Hermit spline interpolation is, or at least I hope so. And I found a method that kind of works, but I'm not sure why, even though I did not look it up or something. I just came up with it myself, but it was a lot of trial and error, and it's kind of weird that I actually found a solution that seems to work. I still want to show you, because just in case that it can be generalized, it would be nice for everyone, I guess. So first of all, I want to prove to you that it really works, or at least prove it as good as possible. And therefore I will just adjust the script so that it has this little section here in ProcessBlock where it goes through all the samples and checks if the absolute sample is greater than 1, and only then it will print to the console that there is an overshoot and the number at which it overshoots. Reload. And now, first of all, you see that nothing is happening so far. But of course, we have to turn up the rate. We can also turn up the width. So we have two signals that do things. And we have a bias parameter, by the way. When the bias parameter is very low, then it will tend to go into the middle, but it can still go outside as much as before. It is just much more rare. And on the other hand, we have bias on 1, which will make it tend to go to the outside as much as possible and only go to the inside very rarely. Maybe we could even just speed up this process by using a way higher frequency. Now we have a frequency that is so high that it actually produces a tone. and we still don't get overshoot from all these points that are measured here. So apparently this method works. But yeah, that's not a mathematical proof, of course. So if anyone has an idea how to get a little bit better proof, then yeah, that would be cool, I guess. Let me just tell you what the script does. Yeah, we have 3 parameters: the rate, so frequency in hertz, the bias parameter, just a normalized one, and the width is also just a normalized parameter, really as easy as it can get. Then we have this object called rand LFO spline that are called LFO. It has a little initialize function and it has a process block. In process parameters, there is also not much going on. We just pass the values to our LFO object. So yeah, that's basically it. And now the interesting bit is the initializing function of the LFO, because that's where we get the overshoot gain compensation, for example. So we init the thing, then we go through all the random values, because there is a 2-dimensional array of random values. The first dimension is the amount of channels that we have, and the second dimension is just the amount of random values that can be there. And this is actually just twice the spline size, and I will explain why that's the case later when we talk about ProcessBlock, because then it will make sense. But that's the dimensions of this array, and we fill it just with zeros. We also give some basic values to the other things. And then we get the overshoot gain compensation, which is the ratio between 1 and this little method here, get max overshoot from the spline, which is a namespace, by the way. So let's just quickly take a look at the spline namespace. It has this little variable size, which just means that the spline interpolator always looks at 4 samples. And yeah, then we have this little process method that just processes the incoming data with some index x, and it does not do the checks whether we go out of bounds or not. It just expects you to give an x that already is like on a legal value. And we have also a process save method that is just the same, but the difference is that it does have these checks. Here's the get max overshoot method. So my approach to this was basically we have a little array called square, and it has the spline size, so 4 samples. So we go through all the samples, we get the ratio so that it's a value between 0 and 1. We rint it, you know, the rint function, then times 2. So we go from 1 to 2, and then minus 1. So we go 2 minus 1 to 1. So we have a square wave. Okay, this is a square wave, but it could also be interpreted as a sine wave if we go do this. And I think that's what the interpolator is actually doing, and that's why we get the overshoot from this. So we have another array and it has the same size. So we go through that array, and now we have this little x. First of all, this is also the ratio, as you can see, but it's twice the ratio. So if we just go ahead and print this to the console really quickly, then we see that this gives us the values 0, 0.5, 1 and 1.5. And for these values, we get minus 1. Let's just draw these. Minus 1, 0, 1, 1.25. And I also tried to make longer arrays, and I noticed then that it would then go back and do this. And then we would get minus 1.25. So this is kind of a sine wave. We actually get this value 1.25 in here. And if we now go back to our method, we have processed this x value on the square wave into our new array. We go through it and get the maximum sample from it and find out it's 1.25. And then we give that back. And now we can actually go back to our init method and see that if we do 1 divided by 1.25, then that equals 0.8. So we could just go ahead and throw this whole method away and just write 0.8 here. But I decided to just keep it there, and I will also upload it like that to my repository so that everyone can see this and like experiment with it and maybe find a way to make this more general for other interpolation types or something, or just to see the thought process. So now we have the overshoot gain compensation, and we can actually start with the implementation of ProcessBlock. We loop through all the samples. for every sample, we increment the phase a little bit depending on the current frequency in hertz and stuff, as if that was an oscillator, you know. And if we go over 1, then we go back to something around 0 again, and we increment the read index. And if the read index is the size of the spline, then we put it back to 0, so we have always a legal read index. And only then we can start looping through the channels, because we want to write something into the rand value array, you know. So basically this means we only write something into the rand value array when the phase has returned, which makes sense because that's how we got the different frequencies into the wave, right? So we go through the channels, get a new value by getting a biased randomized value times 2 minus 1 to get it between -1 and 1, and then times overshoot gain compensation, and that's all we needed this thing for. Now we put the random value into the rand value array, and you remember the rand value array was spline size times 2, so we also put the rand value into read index plus spline size. And this is really cool because we can do this unchecked, because we know it will never go out of bounds because read index can't be higher than spline size. And also it means that later we can use this spline process without the checks. So this is really nice. And now we go back, we have a new random value. Now we have to get an x, which is the read index plus phase plus 1. I kind of forgot why, but you know, trial and error and everything. Yeah, okay, we need a check at this place, but we don't need more checks, which is good. We really only need a reduced amount of checks, and it's less than as if every one of these little uints had a check in the process method, obviously, because it's 4 and it's just 1. So if this is the case, then back below spline size, then we go through all the channels and we put into our data samples array the processed spline from our rand values with the current x. Of course, if you were to use this as a modulator in some way, you would not put this directly into the audio buffer, but you would actually just put an argument here like array double, or since this is 2-dimensional, you would just do this, and then you would basically do the same. You would just have to take samples away and find a new way to give this a name and stuff like that. So let's get back, but you know, this is just for demonstrational purposes. So we just pretend like it is normal to put a modulator into an audio buffer. Actually, that's pretty cool because you could take this and use it as a sidechain signal for sending into another plugin or so, but this is kind of an unusual way to use sidechaining. The bias function, by the way, is also really cool. It is kind of a very resource heavy function because it uses the A10 and 10 thing all the time, and also some multiplications and stuff. It's not too bad, but maybe there's a way to optimize it. But what I like about this function is that it is capable of biasing something more towards the middle, but also more towards the outside, just by getting a little parameter that is normalized between 0 and 1, which makes this really easy to use, in my opinion. Okay, so there you have it. It's a randomized LFO that has no overshoot, hopefully, and it also has no undershoot. It basically has no shoot. It just is perfectly trimmed to the desired range of values, so you can apply it to all your things as a modulator, and you definitely know that it won't be too soft or too hard on the thing, which makes a lot of sense if you want to use it on a buffer that shouldn't go out of bounds or something like that. Alright everyone, see you next time.